Okay, so good afternoon. My name is Alessandro Barbieri. I'm a product manager here at Pluribus, and my job is actually to demystify some of the technology we have and actually make it as simple as possible, hopefully. Let's see if we get halfway there at least. So first of all, I'm going to spend maybe 3-4 slides to explain the platform. This is not about the value of the platform. It tells you underneath the guts of the platform how it works. Okay, some key concepts. There would be a lot to say more, but I think actually we can simplify what the platform is. And then we're going to see what do you do with this platform. Now that you have this infrastructure in place, let's look at how we do virtualization. Let's look at how we do analytics, and let's look at how we do cloud services, right? Cloud services controller. So I'm going to skip this slide because Dave already spoke about it, but there's one concept he mentioned. Merchant Silicon switch as a true extension of the server. I want to focus on this concept because once you understand this concept, you understand why we're a little bit more than a traditional switch. So in this slide up here, I have on my left, I have a traditional switch architecture, dramatically simplified. But the concept is you have a minimal compute and storage infrastructure. Of course, you don't need storage in a network device. That's how it's supposed to be. But the fundamental difference is that any operating system out there managing switches fundamentally is a wrapper around another operating system coming from the merchant silicon vendor. So the operating system really doesn't understand the physical structure of the hardware it's dealing with. There's an intermediary here, the merchant silicon SDK, which is multiple millions of lines of code, completely stateful, which really manages the hardware. This is different from what's happening in a traditional server. In a traditional server, clearly you have more compute and storage capacity, but that's not really the interesting piece. The fact here is that any peripheral device is connected through PCIe and other technology, but let's focus on PCIe for a second, through the control plane, let's say the CPUs. And the server operating system is engineered in a way that everything is direct memory access, the hardware of a NIC. So we took that spirit and actually at Pluribus we did one very simple thing. You have a network interface card connected to PCIe, and we used one of the key invention or disruption happening in the merchant silicon switch space, which is Broadcom and Intel putting a PCIe interface on their chips. Okay, the Pluribus engineers 4 years ago actually pushed, when they were still at Sun Microsystem, those vendors to put a PCIe interface on a NIC. And the reason is, if you do that, now you can control the NIC exactly, the switch exactly like a NIC. So what this means is, the switch chip is fully mapped into the operating system memory. All the table, the register space, and all the learning and the behavior of the switch is completely controlled by the OS. There's no substitute or intermediary, 3-4 million lines of code, completely stateful. So once you do that, now you have a full multi-threading capability on the OS to access the switch. Then you access the switch through a very high-speed interface, gigabit. At what rate can you pump a NIC card? Multi-gig, right? Or even multi-10 gig. This is actually a few megabits, a few tens of megabits in a traditional control plane of a switch. Here we're controlling the switch directly memory mapped. Every time you do a read or a write, you access the chip at multi-gig speed over PCIe. Very fundamental difference. But because you have that, then you can do very interesting things from an analytics standpoint on the switch chip. Then now you're controlling, your OS is fully controlling every aspect of this hardware, and now we can also virtualize it as well, right? It's completely programmable and virtualizable, if you allow me the term, and can be completely virtualized, much like you're virtualizing a NIC through SRIOV technology. And we will see, this is how the technology works. We will see how you can use it later on, right? And then last but not least, we not only control, control the chip through PCIe, but we also have up to 40 gigabit worth of bandwidth to run data plane services on virtual machines on containers sitting on the operating system. So we have a tremendous amount of bandwidth between the control plane processors and the switch chip. Now let's talk about Netvisor. Netvisor is really the crown jewel and eventually the differentiation of this company. The hardware you can actually buy it from most of the ODM or white box vendor. We operate pretty agnostic on any hardware which has an x86 or a Broadcom or an Intel chip. But Netvisor is really the special thing. So what I've done here is I sort of stole a few points from a blog written by Sunay, our CTO, and try to map it on a simple slide. So first of all, it's a type 1 bare metal switch hypervisor. You can visualize it as a sort of a virtual switch with full hardware acceleration, right? That's really what it is. Second is OS agnostic. Our Netvisor compiles as a distribution of Linux, compiles as a distribution of Illumos, or even a BSD. We have done these two. This is actually what we commercialize, and this is more, Linux is more, it's a lab, a proof of concept, but it's not any specific or proprietary operating system. It can be compiled as a distribution of the Unix distribution of your choice. Second is, it's a distributed network operating system. Anything you do on Netvisor, it's not constrained, or the scope is not a single piece of hardware. Everything happens across an entire cluster of devices. Think of it as a Google cluster or a Facebook cluster of computer where multiple devices are glued together by a logic, a control logic to operate as a single device. And we do that not by touching any of the network protocols. We spoke about the high performance switch control plane, which is very unique. And the programmability is truly server style. You're sitting on a server, you're supposed to program the network through C, Java, Perl, Python, exactly like a server. So we expose very powerful APIs, and I'm going to talk about that later on more in detail. And then of course we can run third-party application on top, layer 4 to layer 7 services, orchestration devices. These are full-blown servers. You can run your firewall, your load balancer, and whatnot. We have plenty of bandwidth on the system, and we can also run other types of third-party applications. So that's why we call it a converged SDN platform. A little bit more on this concept. So you have a cluster of these switches. Imagine there's some clustering logic gluing all these together, and Netvisor is really distributed on top of them. What Netvisor does is exposes switches API. So all these switches here are exposed through API, so they can be programmed by anybody sitting on top of this infrastructure. You can sit in a Beehive container. This is a BSD hypervisor, very high performance hypervisor, multi-gig hypervisor that we recommend for layer 4 to layer 7 services. And your Linux program or Linux application of your choice can access a Beehive and the switch API. And the switch API directly. We have a KVM. You can also run Windows on this type of KVM. And we also have our own containers. Those are Illumos-based containers. So process-based isolation or process-based virtualization. We use it internally a lot, but we also allow customers to write their own code, and TIBCO is one example of that. And we have a project to actually move also to support Linux container on top of this platform. So now this is sort of the concept of the platform, okay? So now I want to show you what we can do, some of the things we can do. This is a subset of what we can do with a platform. So we're going to talk about Fabric virtualization, our analytics, and our cloud controller application. First of all, let's demystify how these all appliances and server switches and switches really work. Up here you have a classic leaf spine design. In this case, a layer 2 design I've chosen for simplicity. What we have here is ODM switches, a switch that you can buy from your manufacturer of choice. We have our own branded version of it. And then here we have a couple of network computing appliances, but I could have put those switches also up there. This is a layer 2 design. We support multi-chassis link aggregation, and we build in general a network with open standard merchant silicon-based technology. So we have layer 2 multi-chassis technology, layer 3 ECMP, VXLAN, everything open standard, the spanning tree, the OSPF. We leverage actually Quagga as our layer 3 suite of protocols. At the very basic, Netvisor degenerates to an operating system that runs your network, okay? Now, what can we do on top of this network? We've built a network now we can actually apply our clustering technology. Let me give a quick definition of what is a cluster or a fabric cluster. It's a distributed architecture based on a collection of compute clustering techniques to present an open standard fabric as one logical switch. So this collection of devices, there is a logic that runs over TCP connections between every node and presents the entire cluster as a single logical switch to manage. Interestingly, it's completely distributed and peer-to-peer, so there's no centralized bottleneck or central controller. There's no single point of failure. Every node is a hot plug, so you can lose a switch, you're losing 48 ports of a logical switch. Interestingly, every node has the same view of the network, whether it's a MAC, IP, connection, application flows. It doesn't matter from where you're logged. Anybody has the same view of the network, okay? And most of this information is fetched on demand. If you are asking what are the connections for IP 10.1.1 and those connections are going through this switch will ask the entire cluster and will gather the information. So it's not that we are synchronizing everything through the cluster. It's very selective and very efficient in the way the cluster communicates. And of course, in order to keep sync on this cluster, I mentioned here compute clustering techniques. So this is a 1983 technology, the classic, the three-phase commit technology used in database clusters to keep those in sync. The way it operates is very simple. Once you commit a configuration change, either every node in the cluster agrees that this is a change that they can accept, or the change never actually takes place. So always in sync for the stuff that matters.
What are your limitations in clustering? How many nodes are you limited to, or is there a limit?
Yeah, so this is a question I replay the answer that our CTO says. So it's completely distributed, right? Practically, and I have to be a little bit prudent here because practically we haven't built thousands of nodes. But when they were at some microsystem, they built with this technology cluster of hundreds of machines. Now, are we going to scale to hundreds of machines? I'm not sure, but we haven't found any practical limitation up to 50. And our simulation, they think they can scale in excess of 300-400. But again, we don't have the deployment to prove 300-400 type of scale. Again, we find that our customers are happy between anywhere 4 and 12 racks. And this technology, 24, 50 switches is like a joke. Because again, in order to keep state, you have a TCP connection to every other node in the cluster. A modern server can handle roughly 500,000 TCP connection without blinking, okay? And that's what we have here, right? So now we'll build a layer 2 network, we'll build the clustering, you get some of these benefits. One of the major benefits, at least in my view, is the ability actually now to have full visibility fabric-wide or cluster-wide, I should say, of everything that's going through the network. I don't have time to cover this, but this is alone is a huge chapter. We could spend an hour on that. Fundamentally, what I've put here is a couple of high performance appliances with the Fusion I/O flash storage, because with Fusion I/O flash storage, we can record analytics in real time. I can write at roughly 10 gig speed all the events happening through the network. We can do time machine, and you will see time machine in action later on. It's the ability to record the state of the network at any point in time, and then you can perform troubleshooting maybe a week ago, 2 weeks ago. You can check the connection of server A to server B. Was it particularly slow 5 weeks ago at 3:22 p.m.? What was going on? You can check the connection and evolve full statistics across time, as well as the physical cluster. Application flow analytics, we can capture actually flow throughout the cluster. You can program any switch in the cluster to capture a particular flow, and you can sort of start recording those flows, and I think you will see a very interesting demo later on. And then one of the most interesting aspects is that anything that's happening on virtual machine or physical host is treated exactly the same way. So we have full visibility into physical and virtual traffic. We can also do this application flow analytics inside a VXLAN tunnel. And you will see some of that as we go forward. Speaking of analytics, it seems like a black magic. It's really not, right? You have seen a little bit how our architecture operates internally. So we have this multi-10 gig connection between the CPUs and the switch chip and the CPUs. This is what we're really using to intelligently select which traffic needs to go to the CPU for analytics. So what we do is we look for particular flags in a TCP connection, a SYN, a FIN, and those flags trigger the packet or a flow to actually hit the CPU. But only one packet. Then we record it, create an entry in a hash table. We can actually dump the hash table either in our RAM or in a Fusion IO, very fast flash storage. And then at that point, we just keep reading very fast the different counters and congestion information from the chip. When the information age out, we actually transport it on more colder storage, such as the SSD that we have on board. We can have actually multi-terabit SSD. You can deploy analytics in line. This is ideal, right? You buy the network, you get the analytics as part of the network. But many customers are not comfortable just ripping out an entire network right away. So what they do is perhaps deploy some of the Pluribus switches, and then they use mirror ports or taps to redirect traffic from a regular switch, from a normal switch into our device. And we can also perform in mixed mode. We are both a passive listener. We don't switch traffic that comes from a mirror port, as well as in line. And we can also be a bump in the wire, just a layer 2 device that sits in between 2 layers of network. And those are actually real deployment customers who have done that. A customer said, "Are you crazy? I'm not going to rip out my Cisco network, but you know what? Let's see how you behave, and we'll start from there." So we're actually as just an analytics appliance, which is actually very interesting. Okay, now we build the cluster. We can do the analytics. Now let's virtualize the cluster. So this is your cluster. This is the sort of single logical view. And then we have our hypervisor software that sort of kicks in and allows you to do the following. Let's say you want to create a red network and a blue network, right? The red network has a slice of the physical resources across the cluster. So in this case, you can say, hey, I want the red network to have 100 VLANs, 1,000 VXLAN IDs, 16K max. Remember, we do everything in software and we use the hardware as a cache. So we have a complete flexibility in the way we define even table sizes for this virtual network. And then I'm going to take, let's say, port 1 through 16 from different switches across the cluster. And you have ample flexibility to redefine, to define exactly that. And let me create the blue network. Again, you give in physical resources, network resources, and you effectively are creating a slice in that network of the resources. That's your blue network. Then you can create the green network. I had no space, so but anyway, you can create a green and.
By default, what are customers using? Do you support just traditional VLANs everywhere, traditional L3 in the spine, or do you?
Exactly. The very first slide I showed you is we start off by building a layer 2, layer 3 network. I use L2 multi-lag chassis, spanning tree, ECMP, BGP, all the Quagga protocols. I can do VXLAN. This is the connectivity layer, right? Then on top of it.
But I'm saying, do you need VXLAN in the solution?
We don't need VXLAN necessarily, right? You want to use VXLAN, we operate with VXLAN as well, right? VXLAN is the data plane isolation, right? VLAN and VXLAN is at the data plane level. When the packets hit the wire, you actually distinguish between red network and blue network, because red network is associated with a specific range of VLAN. I'm not touching your frames, I'm not touching your packets, I'm not inventing any new protocol here. This is a sort of a management construct that allows you to isolate the infrastructure, carve the infrastructure in multiple slices, and what you then can do.
So are you bridging there? In that example, are you bridging VLAN to VXLAN?
We can also do that. We have VTEP functionality, right? So if you have VXLAN here, we can actually, and you have some physical workloads and virtual workloads, we can actually do the VTEP function or the gateway function on our switches itself within a particular VNet. Yes, we can. But the point here is, it doesn't matter, now that you have created those slices of the infrastructure, whether you have a physical server or a virtual machine, as long as you're connected to a green port or a blue port, you only see the blue network or the green network or the red network, okay? And we allow at that point...
I understand having blue, red, and green ports on the access layer. Why do you seem to have them at the spine?
Those are actually resources which are allocated.
That is not blocks of ports.
Yeah, that are allocated across the network. And frankly, the port here is more an example. You don't need to separate those virtual network by ports. You can actually do a VLAN separation and have a trunk out of a port here which takes the blue, the green. But for illustration purposes, I want to show the idea of carving the infrastructure into a slice. And then once you've done that, you can associate different services running off of our appliance or not to different networks. So for example, we run routing, NAT, Pixie server, DHCP, DNS, and you can create multiple virtual instances running off of our platform and associate those to a particular network. And those networks can be managed through role-based access. So this guy can be your VMware administrator. This guy can be, I don't know, your network administrator, and they can coexist on the same infrastructure and manage it. Everybody's managing his own sort of slice.
When you talk about slices, are you doing things like VRFs underneath?
We're doing only VLANs and VXLANs at this point. We don't have the traditional concept of VRF.
So right now, if customer A or Red has 5 VLANs,
yes.
Where will you perform inter-VLAN routing for those VLANs?
Yeah, so we do have routers. One of the services that we have on this platform is a virtual router. Every box here can have up to 16 of these virtual routers.
Are you talking about, within the compute portion of the box or native on the switch?
It's native on the switch. It behaves like a normal router, but it's more of a sort of a virtual instance, and you can have 16 of them operating independently, each managing different sets of VLANs or different sets of tenant networks.
Are those routers in top of rack, or are they aggregated in the spine?
You can choose, because we can run layer 3 here, or you can run layer 2 and layer 3 demarcation up here. In this example, I have the router running up here, right?
But I'm saying if you had 20 racks, are you doing L3 in every rack? Or do you have to pick like 2 racks where you're doing L3?
Yeah, okay, so it really depends how you're designing your network. If the demarcation, layer 3 demarcation is here, you want to do maybe routing at every node. Instead, if your layer 3 demarcation is up here, you want to do layer 3 and routing VRP up here, and then you keep a clean layer 2.
Well, I guess that's the question. Are you, if you're doing L3 in top of rack, can you have every rack host the same default gateway for the servers?
The same default gateway. Yeah, I mean, at that point, if you're designing layer 3 here, this is your default gateway for the rack.
I don't know, but you're pointing at one rack. I'm just saying, if you have like 10 racks.
Yes.
Are you doing VRP, or is there something else within the Pluribus fabric?
We have VRP to do gateway load balancing.
Is there a limitation then? Is it active standby? Is it, again, across a large data center, L3 and top of rack? Yeah. Do you route locally in every rack within that VLAN segment or whatever segment technology that is being used?
Yeah, we can route we can route inside every rack. Yes.
For the same tenant.
Yes.
With VRP though, that seems like
I don't know where VRP comes in.
VRP if you have two top of racks.
I'm saying 10 or 20 larger.
Oh, okay.
You got like 50 racks, right?
Yeah.
Pepsi has 2 VMs. One's here, one's way down there. They're both on the same logical bridging segment, right? They need to get processed by the exact same default gateway IP address. Can that happen?
Can it happen at the spine level? Or
to these questions, let me come on there, and then we have a whole session on just deep diving.
Basically, just a distributed gateway.
Right.
Let's deep dive it in 5 minutes.
Rock on. Thank you.
Okay. Okay, and once you have all this, what we can do is also actually use OpenStack to manage the entire infrastructure, right? So one of the things we do on this platform is we have a sort of I call it here, out-of-the-box, hassle-free OpenStack configuration, so you can just focus more on managing your network and your workloads. We take care of actually coordinating the entire OpenStack infrastructure right out of the box. So pre-install and pre-configure, ready to deploy your virtual machines in a matter of minutes. We manage storage, we manage the services through OpenStack, and of course you can deploy those tenant networks through an OpenStack interface.
Is that a certain distribution that you support?
Yes, right now we're sitting on the Havana and the CentOS, built-in CentOS, but we have also a partnership with the Red Hat, so we also integrate with the Red Hat OpenStack platform. And there's another partnership with Oracle to also have their version of the OpenStack controller to manage our infrastructure. Okay, and last, we can also extend Netvisor into the microblade or the microservers. So the microserver, if you guys have time, you can see it in action live in our mini data center upstairs. It's a 6CU chassis, the model we have here. There are 112 servers distributed on 28 sledges. They call them sledges. And then on the back, there are 4 switches. Those are switches. Each switch is running an Alta chip, and those 4 switches can be connected through active-active multi-chassis lag through top of racks, right? That's the example here. And now you can, the same virtualization, the same OpenStack that we discussed actually can be extended all the way down to inside the rack to the microblade chassis. Okay, so explosion of number of nodes, but again, we can manage those nodes effectively as a single logical device, which thanks to the clustering technology. And all the features I discussed before can now be applied to this rack of compute with integrated network.